You train diffusion models. They're thought too weak for high-quality images. You connect them to denoising score matching. Suddenly, the loss aligns with Langevin dynamics. You simplify the variational bound. It focuses on harder denoising tasks. You train on CFAR 10. FID drops to 3.17, beating most Jans. You test on 256 by 256 LSUN. Samples match ProgressiveGAN's quality. You dig into the math. Realize they're not just Markov chains, they're generalized autoregressive models. With a noise-based ordering no coordinate swap can mimic. You try progressive decompression. Large features emerge first, details last, like a universal image builder. You check the numbers. Log likelihoods aren't best, but sample quality soars, half the lossless bits, wasted on imperceptible details. You realize it's not just a generative model, it's a bridge between nonequilibrium thermodynamics and the art of creating images from noise. You didn't build another sampler, you built a framework where diffusion, score matching, and compression meet as one.
Wow, okay. Well, that was certainly an unconventional, very energetic opening for a deep dive into advanced machine learning. I think I need a moment.
Just trying to capture the excitement, it really felt like a series of breakthroughs.
It really did, and you absolutely hit on the key points.
Yeah.
Today, we're unpacking denoising diffusion probabilistic models, DDPMs.
DDPMs, yeah.
For years, I mean, seriously, these models, which are inspired by something pretty fundamental, non-equilibrium thermodynamics, they were kind of seen as theoretical curiosities, almost a running joke in some research circles, you know?
Really? A joke?
Oh, yeah. Like diffusion models? Oh, sure, they're great for theory papers, maybe, but not for actually making pretty pictures. There was this real feeling they were just, well, too weak for high-quality image generation.
Okay, so what changed? Because obviously now they're everywhere.
Exactly.
Yeah.
Then came these aha moments you mentioned, these key innovations that just completely flipped the script, like connecting them to denoising score matching.
Right.
And realizing that the training laws suddenly aligned with something called Langevin dynamics.
Yeah.
It was like finding the keys to this universal image builder people had only dreamed about.
A universal image builder. I like that.
Yeah. Starting from pure noise, pure static, and just sculpting it into stunning realistic images. So our mission today in this deep dive is to really pull out the most important bits of insight from that core research paper, Ho, Jain, and Abbeel, NeurIPS 2020.
Got it. The foundational paper.
Right, along with a study guide and a timeline we looked at. We want to show you how they went from these theoretical things to state-of-the-art image generators.
Okay, let's unpack this for everyone listening. You mentioned they turn noise into images. But what is a diffusion model at its core? You hear Markov chain, noise. Is it just like reversing a blur filter, or is it more complex?
That's a great way to put it. It's definitely more than just reversing a blur. At its heart, a diffusion probabilistic model, a DDPM, it's a type of latent variable model.
Latent variable, okay.
Think of it like a really sophisticated system that's trained to do one thing very well, reverse a process. Specifically, a process that gradually adds noise to data step by step.
That's noise. Okay, why would you do that?
Well, stick with me. The whole point is to learn how to undo that process, to produce these incredibly high-quality samples that look like they came from the original data distribution. Basically, learning to sculpt meaningful images out of pure randomness.
Sculpting from noise. Okay, I'm starting to get it.
Yeah, and it happens in two main parts, like a dance almost. First, you got the forward process, or the diffusion process.
The noise adding part.
Exactly. And this part is fixed. The model doesn't learn this part. It's a predefined Markov chain. Imagine taking a clear photo, right? And step by step, over, say, t time steps, you add a tiny bit of Gaussian noise.
Okay.
It gets a little blurrier, a bit noisier each time until time step t, xt. It's just pure noise, undifferentiated static.
Like an old TV screen with no signal.
Pretty much. And what's really useful here is that mathematically, you can figure out what the noisy image extract looks like at any step directly. It's a closed form equation. Makes training much easier.
Ah, efficient.
Right. And the amount of noise added, these aught values, they're usually just set beforehand. Constants.
Okay, so that's the forward noise in process. What about the other direction?
Right, that's the reverse process. And this is where the learning happens. It's also Markov chain, but its transitions, how it moves from one step to the next, are learned.
Learned how?
It starts from that pure noise state, xt, what we call standard normal prior. And it learns step by step to reverse the noise addition, to take that static and gradually remove the noise, aiming to get back to a clean sample.
X0. So it's learning the sculpting part.
Exactly. It's like watching that sculptor, starting with a block of marble, the noise, and carefully chipping away until the statue of the image emerges.
That's a great analogy. Okay, now, The paper talks about this huge deal, this novel connection between these models and something called denoising score matching with Langevin dynamics. That sounds intense.
It is intense, but it's also where the magic happened. This connection is arguably the single biggest reason DDPM suddenly became so incredibly good.
Okay, break it down for us.
So Ho, Jain, and Abbeel, they showed that if you set up the math, the parameterization of these diffusion models in a very particular way.
Parameterization meaning like how the model represents things internally.
Exactly. How you define the learned parts. If you do it right, it turns out the whole training objective becomes mathematically equivalent to something called denoising score matching, but done across many different noise levels simultaneously.
Denoising score matching sounds like matching scores to remove noise?
Kind of. Score matching is about learning the gradient of the data distribution. Basically, teaching the model which way to push a noisy point to make it slightly less noisy, slightly more like the real data. Denoising score matching does this specifically for noise removal.
Okay, and Langevin dynamics, that sounds like physics.
It is. Langevin dynamics describes how particles move around randomly due to heat, but also drift towards lower energy states. When you sample from a trained DDPM using this specific setup, the step-by-step denoising process actually mathematically resembles annealed Langevin dynamics.
Annealed, like cooling down.
Yeah. Precisely. Imagine slowly cooling a system so particles can settle into the most stable configuration, the lowest energy state. Here, the lowest energy state is basically the clean, high-quality image.
Wow. So the sampling is like physics finding the best state.
In a mathematical sense, yes.
Yeah.
And this wasn't just a cool observation after the fact. This theoretical link directly guided how they designed the model. They realized training the model using variational inference was actually optimizing a sampler that behaved like Langevin dynamics.
So theory led directly to better design.
Absolutely. A key example is how they parameterized the mean of the reverse process. Instead of predicting the mean directly, they chose to predict the noise that was added at that step, the prediction parameterization.
Predicting the noise instead of the signal.
Seems counterintuitive,
What?
right? But it dramatically simplified the math, the variational bound they were optimizing. And crucially, experiments showed it worked incredibly well. It's a beautiful example of deep theory unlocking practical performance.
Okay, that makes sense. Theory points the way. But then they did something else. They simplified the training objective, called it L-simple. Why simplify if the theory was so elegant? Doesn't simplifying usually mean losing something?
That's the fascinating part. It seems counterintuitive. But this simplification was another stroke of genius, driven more by empirical observation, by what actually worked in practice.
So L-simple, what did it do differently?
Right, so L-simple is basically a simplified version, a wording variant, of the standard variational lower bound VLB objective typically used for these kinds of models.
Weighted. How so?
It effectively downweights the importance of the loss terms corresponding to small values of t.
Small t meaning the steps where there's only a tiny bit of noise.
Exactly. When the image is already almost perfectly clean, L-simple basically tells the model, look, don't sweat the small stuff, don't spend too much capacity trying to perfectly denoise an almost perfect image.
So it lets the model focus its effort elsewhere.
Precisely. It allows the network to concentrate on the harder denoising tasks, the steps where it is larger, where the image is much noisier and requires more significant reconstruction work. It's like telling the sculptor, focus on the main shape first. Don't worry about polishing the fingernails until the arm is carved.
Okay, that makes practical sense. Prioritize the hard parts.
And it worked wonders for sample quality. They also found empirically that fixing the variances in the reverse process to be time-dependent constants rather than learning them also improved sample quality and made training more stable.
So A prediction plus L-simple plus fixed variances. That was the magic combo.
That was the combination that gave them their best results, yeah, including that FID score of 3.17 on the CFAR10 dataset.
And FID, that's the fresh at inception distance, right?
Yes.
Measures realism and diversity.
Correct. Lower is better. And 3.17 was a big deal back then, beating most GANs, which were the reigning champs of image generation at the time. It really showed that smart, empirically driven simplification can sometimes be just as powerful as pure theory.
Okay, so the results were impressive. You mentioned FID beating GANs, matching ProgressiveGAN on LSUN. The pictures look amazing in the paper. Celeba faces those LSUN churches.
Oh, absolutely. The visual quality was undeniable. That 3.17 FID on CFAR10, that wasn't just a number. It meant the generated images looked incredibly realistic for that data set. And doing well on 2x6 by 256 LSUN, these complex scenes, that showed it wasn't just a fluke on small images. It really put diffusion models on the map as serious contenders for top-tier image generation.
But then there's this twist you mentioned earlier about log likelihoods.
Right. This is one of the most interesting findings, I think. Despite this incredible sample quality images that look fantastic to us, these DDPMs did not achieve competitive log likelihood scores compared to other models specifically designed for likelihood estimation.
Wait, log likelihood measures how well the model assigns probability to the real data, right? Like how well it could compress it?
Exactly. High likelihood means the model thinks the real data is very probable, which usually correlates with being a good lossless compressor. If you wanted to compress the original data set perfectly, bit for bit, without losing anything, other models were better.
So the DDPMs make great-looking pictures, but they're not technically the best at explaining the original data pixel perfectly.
That's the core insight. And the author's conclusion is brilliant. They propose that DDPMs have an inductive bias, a built-in preference, basically, that makes them excellent lossy compressors.
Lossy, meaning they throw away information.
Information that we as humans might not even perceive. They argue that a huge chunk of the information needed for perfect lossless compression, maybe more than half the bits, describes imperceptible image details. Tiny variations, noise patterns, stuff our eyes just don't care about.
So the model learns to ignore that stuff.
It seems to prioritize what looks good, what's perceptually important, overachieving perfect mathematical fidelity to every single pixel. It's like that brilliant artist analogy, again, capturing the essence, the visual impact, without getting bogged down in microscopic details.
That makes you think about perception itself, doesn't it? Maybe our own vision is inherently lossy in a way.
It really does raise those kinds of questions. Are these models succeeding precisely because they align better with how humans perceive quality? It's fascinating.
Okay, so they're great lossy compressors that build images.
Yeah.
You also mentioned progressive generation. How does that actually look? And what's this link to autoregressive models?
Right. The progressive generation is something you can actually see if you watch the reverse process happen step by step. When the model starts generating from pure noise, XDDT, the first few steps, XD for large T, produce very blurry coarse features.
Like the basic shapes.
Exactly. You might see the rough outline of a face or the general structure of a building. Then, as air decreases, as the model takes more denoising steps towards X, finer and finer details gradually emerge. Edges sharpen, textures appear, colors become distinct.
Like focusing a camera lens?
Sort of, but it's more like building the image up. The paper calls it a progressive lossy decompression scheme. The most crucial, large-scale information needed to understand the image appears first, followed by the refinements.
And the autoregressive connection, how does that fit in?
This is another neat theoretical link. They showed that the math behind the DDPM's variational bound can be rewritten in a way that looks very similar to training an autoregressive model.
Autoregressive models, those generate things sequentially, right? Like pixel by pixel or word by word.
Typically, yes.
Ah.
They rely on a fixed ordering, generate this pixel, then the next one based on the first, and so on. The diffusion model, specifically Gaussian diffusion, acts like a generalized autoregressive model. The ordering isn't fixed pixel coordinates. It's defined by the noise levels.
A noise-based ordering.
Yeah. And the author suggests that maybe this Gaussian noise process is a more natural way to structure the generation of image data compared to the somewhat arbitrary pixel by pixel or block by block masking used in some traditional autoregressive models. It seems to lead to better overall sample quality.
So it's like a more flexible, image-friendly way of building things up step by step.
That's a good way to think about it. And it ties into the latent space, too. Even the intermediate noisy images, say by 750, which looks like static, actually contain high-level information.
You mentioned that gender, hair color, pose, hidden in the noise.
Hidden in the noise, which is amazing. It means the latent space is structured meaningfully, allowing for smooth interpolations. You can morph one generated face into another and see attributes like hairstyle, expression, even background change plausibly along the way. It shows the model isn't just memorizing. It's learned a deep semantic representation.
We've certainly covered a lot of ground today, really gone deep into these denoising diffusion probabilistic models. It's just amazing how they went from being, well, almost dismissed to becoming these absolute powerhouses in AI image synthesis.
It really is a fantastic story of innovation, isn't it? We've seen how those key insights, that connection to score matching and Langevin dynamics, the cleverness of the L-simple objective, focusing on perception, understanding them as lossy compressors, just completely changed the game.
They really did build that framework you mentioned at the start where diffusion, score matching, compression, it all comes together. That idea of a universal image builder from noise feels much more real now.
Absolutely. It fulfilled that vision in a way few might have expected just a few years prior.
So wrapping up, what's the big takeaway for everyone listening? You've definitely got a shortcut now to understanding one of the most exciting shifts in recent AI, but maybe there's one more thought to leave people with.
Well, building on that idea of lossy compression and perceptual quality, if these incredibly successful models inherently learn to prioritize what looks good to humans over perfect objective data reconstruction, what does that really tell us about our own perception? How do we process visual information? How much detail do we discard? And looking forward, as this art of creating images from noise gets even better, how will it continue to shape our reality, blurring those lines between what we see generated by AI and what we see in the real world?
That's a deep question to ponder, a perfect note to end on. Thanks so much for unpacking DDPMs with us today.
My pleasure. It's fun diving in.